everyone. In the previous class, we discussed about the elastic analysis of the circular tunnel. We saw the stress distribution around the circular tunnel, and also we saw that how the deformations or the displacements are going to occur. That was followed by our discussion on the analysis of the concrete lining, and that was also the elastic analysis. So, today we will start with the elasto-plastic stress distribution around the circular tunnel, and here we will take the help of Tresca yield criterion in order to define the plastic region of the rock. Let us see how we proceed in this direction. This resembles to a problem of circular hole in an infinite plate. In case of the incompetent rocks which are sufficiently plastic to deform without fracturing, such elasto-plastic situation will be relevant. Rocks such as shales, phyllites, slates, limestones or dolomite, they exhibit elasto-plastic behavior, especially at high temperature, pressure and depths. So, this figure shows the geometry of the problem. You see that this is what is the ground condition. Here this is the intact rock, and in this rock you have made the excavation in the form of this circular opening which has a radius of A. Then because this rock is in such a way that there is the occurrence of a plastic zone all around this cavity which is the circular tunnel, and that has been represented by this blue colored curve. It has been assumed to be more or less circular. Why is it so? We will discuss that in detail just in subsequent slides, and the radius of this zone from the center, that has been taken as C. So, the rock which is beyond this boundary, this is in elastic zone, and the rock in between the boundary and the cavity, this is in the plastic zone. So, this is what we call as the intact rock, and here in this plastic zone, that is from here to here, you will have the loosened rock. So, this boundary which is drawn with the help of the blue color is the boundary between the elastic and the plastic zone, and therefore, we call this as elasto-plastic boundary. As we discussed in case of the elastic analysis, in this case also any point in the rock is denoted by r comma theta, where r is its radial distance from this center point O, and theta is an angle which is measured from the horizontal in the anti-clockwise direction as shown in this figure. Coming to the loading condition, it is assumed that there occurs the hydrostatic in situ state of stress. That means that the vertical as well as the horizontal in situ stresses, they are same. All the basic equations such as equations of equilibrium, compatibility and strain displacement relationship, all these must be satisfied. Rock surrounding the periphery of the cavity to some extent gets loosened and yield, and this results into the development of a plastic zone, as I just explained you when we were discussing about the geometry of the problem. And C is defined as the radius of boundary between elastic and the plastic zone. Coming to some discussion on the plastic zone, the state of stress which is developed is such that it equals or exceeds the yield stress of rock immediately surrounding the periphery of the cavity. What does that mean? That is, the material yield condition is satisfied, and therefore the surrounding rock enters into the plastic state up to a radial distance of C, which we are calling as elasto-plastic boundary. This elasto-plastic boundary is circular. Why? Because the geometry, loading and the boundary condition of the problem, they all are symmetric. So, for all those conditions like condition of equilibrium, compatibility condition, everything should be satisfied. So, this elasto-plastic boundary has to be circular. We are assuming this elastic perfectly plastic response of the rock, which is characterized by a yield stress, and it is assumed that rock which is immediately surrounding the cavity, it follows the Tresca yield criterion. It is not necessary that it follows the Tresca yield criterion, it can follow more Coulomb failure criterion as well. But here, as far as this lecture and the scope of this course is concerned, we will be restricting only to the Tresca yield criterion. However, the procedure that I am going to explain for the elasto-plastic analysis is general enough, and you can apply any failure criterion to represent the rock immediately surrounding the cavity. Coming to the material properties, beyond the elasto-plastic boundary, the surrounding rock will behave in an elastic manner, as we have assumed that the rock is following Tresca yield criterion, which is the maximum shear stress criterion. Take a look at this figure, where sigma versus epsilon has been plotted. Up to the elastic limit, it goes in a linear fashion in this manner as shown here, and once it enters, or once the material yields, then it enters in the plastic domain, and this is how the stress strain relationship will be represented. So, here you get the maximum stress, which is the yield stress, and it is represented by sigma equal to sigma y. So, what is the state of stress in this case? Let us see that. That is going to be sigma r, sigma theta and tau r theta, which will be equal to 0, and you will have sigma z for tunnel in a state of plane strain. Then in the elastic zone, we have the stresses as sigma r prime, sigma theta prime and sigma z prime. and in the plastic zone these are represented as sigma r double prime, sigma theta double prime and sigma z double prime. Now, what will happen to the yielding condition in the elastic zone is half sigma theta prime minus sigma r prime will be equal to kappa. And when this condition is satisfied, we would say that the yielding is taking place, and then we can write this equation in this form that sigma theta prime minus sigma r prime is equal to 2 kappa. This is equation number 1a. What happens in plastic zone? We will have half sigma theta double prime minus sigma r double prime, that would be equal to kappa. Here it is the yielding which is continuous, or we can write it in this particular form, this equation as sigma theta double prime minus sigma r double prime, this is equal to 2 kappa. This is equation number 1b. Now, what are going to be the equations for the equilibrium in the polar coordinate systems? So, here we have del sigma r del r plus 1 upon r sigma r minus sigma theta plus 1 upon r tau r theta del tau r theta del theta is equal to 0, and we will have 1 upon r del sigma theta del theta plus del tau r theta del r plus 2 upon r tau r theta is equal to 0. Now, we have seen that since tau r theta is equal to 0 and due to symmetry, no change in the stress which is in theta direction. So, this is going to give me del theta of sigma theta will be equal to 0. So, in the plastic zone, what will happen? Del r of sigma r double prime. Please remember that when we are representing the state of stress in the plastic zone, we are representing them by double prime plus 1 upon r sigma r double prime minus sigma theta double prime. This is going to be equal to 0 because tau r theta equal to 0. So, this is going to give me del r of sigma r double prime. This will be equal to 1 upon r sigma theta double prime minus sigma r double prime. This equation I am marking as equation number 2. What will happen in case of the elastic zone? Similarly, I can apply that equation of the equilibrium. So, we are going to get del r of sigma r prime will be equal to 1 upon r sigma theta prime minus sigma r prime, that is equation number 3. Now, what will be the compatibility condition in the elastic zone? So, that will be given by del 2 del r2 plus 1 upon r del r, and this whole operator will act on sigma r prime plus sigma theta prime will be equal to 0. This equation is going to be equation number 4. Now, these equations of equilibrium and the compatibility equation are to be satisfied subjected to boundary condition of the problem. So, we have here boundary conditions. So, take a look at this figure. This boundary, that is at r equal to a, it is the free boundary because here excavation has taken place. So, this is the boundary of the cavity. So, therefore, what we will have here is that sigma r double prime will be equal to 0. Now, at the elasto-plastic boundary, what is R at elasto-plastic boundary, which is this elasto-plastic boundary? What is R here? That is at R equal to C. There is going to be the continuity of the stresses across this boundary. Okay. So, because of that, what you are going to have is sigma r double prime r equal to C minus, which is going to be equal to sigma r prime r equal to C plus, and sigma theta double prime r equal to C minus is equal to sigma theta prime r equal to C plus. Please understand that here this is the elasto-plastic boundary, and for this system to be in equilibrium, there has to be the continuity of stresses across this boundary. Now, this, when I say r equal to C minus, that means we are somewhere in the plastic zone, but very near to this elasto-plastic boundary. When I say r equal to C plus, we are in the elastic zone, but again we are near to the elasto-plastic boundary. That is what is the meaning of these r equal to C minus and r equal to C plus. That is, we are at the boundary, but just inside and just outside the boundary, what exactly is going to happen. So, this equation I am calling as 5b. Why we are writing for r equal to C minus sigma r double prime? Because when r equal to C minus, we are in the plastic zone, and in the plastic zone we are representing the state of stresses with double prime. Now, the next boundary condition is that at sufficiently large distance from the periphery of the cavity, what will happen? What does this mean? That I say that r is tending to infinity. We have seen in case of the elastic analysis that at r tending to infinity, the stresses are going to be equal to the in situ stresses. So, that we can write as that sigma r prime r tending to infinity will be equal to sigma theta prime at r tending to infinity, which is equal to p. Make this equation at 5c. When I say r tending to infinity, essentially this is going to be in the elastic zone, and therefore the state of stresses are being represented by single prime. This p is the applied hydrostatic stress. What is A? This is the radius of the cavity, and C is the radius of boundary between plastic and elastic zones, as it has been shown in this figure. Now, coming to the solution of these. So, these solution will involve the solution of equations of equilibrium, which were given by equations 2 and 3 and subjected to the boundary conditions which we just derived, which are equation number 5. So, what we will do is we just substitute these yield condition given by 1b in equation number 2. What we get is del r of sigma r double prime is equal to 1 upon r into 2 kappa. This is 6a. Now, you integrate this equation. So, integrating equation 6a, we are going to get sigma r double prime, that will be 2 kappa ln r plus a prime. Now, from equation number 5b, what is your sigma r prime at r equal to a? That is what is your equation number 5b. So, we have 2 kappa ln of a plus a prime, this will be equal to 0, and therefore, from here we can determine this a prime as minus 2 kappa ln a. Now, substitute it here in this expression, and what you will get is sigma r double prime will be equal to 2 kappa ln of r upon a, because this minus sign will make this a to the power minus 1, and this term can be combined. So, this equation I am making it as 6. Now, I substitute this equation number 6 in equation 1b. So, we will be getting sigma theta double prime is going to be 2 kappa 1 plus ln r upon a. This is equation number 7. Now, what will happen in case if you have the elastic zone, you will have the stresses in this form, that is sigma r prime is A plus B upon r square, this is 8A, and sigma theta prime is A minus B upon r square. Please refer to our discussion related to the elastic analysis. There we derived these expression for sigma r and sigma theta, and if you just correlate, they were in this particular form. So, I am directly taking it from there. Now, we substitute the boundary condition at r tending to infinity. So, substituting the boundary condition at r tending to infinity. So, what will happen? What is that condition? We have written sigma r prime is equal to p. So, when this r is tending to infinity, this term will become very large tending to, because r is tending to infinity, and this whole term will tend to 0. So, therefore, this will become equal to A. Okay. Now, substituting this boundary condition at the elasto-plastic boundary, which is at r equal to C. So, what was that? Sigma r at r equal to C plus, this was equal to sigma r prime, because when it is C plus, we are in the elastic domain, and this is going to be equal to C A is equal to P. So, I will have P plus B upon C square, and this is going to be equal to sigma r, r equal to C minus, which is equal to sigma r double prime, and this will be equal to 2 kappa ln C upon A. We just obtained this. So, make this equation as 9A. Similarly, we have it for theta, sigma theta r equal to C plus, that is going to be equal to sigma theta prime, and this is what is your P minus B upon C square. This is equal to sigma theta at r is equal to C minus, which is equal to sigma theta double prime, and this is going to be 2 kappa 1 plus ln C upon A. This is 9B. Okay, so this is how we obtain the expression for sigma r double prime, sigma theta double prime, and the respective stresses in the elastic zone as well. Now, if we look at equation number 9A, this will give me B upon C square is equal to 2 kappa ln C upon A minus P, right, and 9B will give me P minus 2 kappa ln C upon A plus P, that is going to be 2 kappa 1 plus ln C upon A. Or what we will have, see, throughout this 2 will get cancelled because this P and this P will make it 2P. So, ultimately we will have P minus kappa ln C upon A is equal to kappa 1 plus ln C upon A. So, from here we can write that P upon kappa is equal to 2 ln C upon A plus 1, or I will have 2 ln C upon A is equal to P upon kappa minus 1, and this also can be written as ln C upon A, that is P minus kappa upon 2 kappa, and from here I can get C is equal to A exponential of this quantity, which is P minus kappa upon 2 kappa. So, this is how the radius of this elastoplastic boundary is obtained in terms of the other quantities. And therefore, what will happen to this B? That is going to be now C square. You have 2 kappa ln C upon A minus P. So, we just substitute the expression for this C. So, this is what that we are going to get A square e to the power 2 P minus kappa upon 2 kappa, and then this quantity, that is 2 kappa ln C upon A minus P. So, just solve this. So, this 2 and this 2 will get cancelled out. So, ultimately what you are going to get here is A square e to the power P minus kappa upon kappa, and here again here I substitute the expression for C. So, 2 kappa ln then A e to the power P minus kappa upon 2 kappa, this whole thing divided by A minus P, and here this A will get cancelled out, and you see here this is ln and exponential. So, this term will now can be written as A square e to the power P minus kappa upon kappa into 2 kappa. It will simply be P minus kappa divided by 2 kappa minus P. So, ultimately we are going to get a simple expression for B as minus kappa A square e to the power, or let me write it in the exponential form, that is P minus kappa upon the kappa. This equation I will write as equation number 10. And I already have the expression for C as A exponential of P minus kappa upon 2 kappa, that is equation number 11. So, this basically defines the distance to the elastoplastic boundary, and this is a function of P, kappa and A. So, this yield shear stress which I am representing by this kappa will be some fraction of this applied stress, which is P. So, I assume that this kappa is equal to some fraction h of this applied stress P. Make it equation number 12. So, for tunnel to be in a state of plane strain, remember we are doing this derivation for this situation, this sigma z prime will be equal to nu times sigma r prime plus sigma theta prime, and sigma z double prime is going to be equal to 0.5 times sigma r double prime plus sigma theta double prime. Now, why this 0.5? That in the plastic state your material becomes incompressible, and you know that for an incompressible material nu can be taken as 0.5. So, let us try to write the complete solution here. First I write in the plastic zone, that is A less than or equal to R less than or equal to C. Your sigma r double prime is given as 2 kappa ln r upon A. Sigma theta prime is 2 kappa 1 plus ln r upon A. Sigma z double prime is kappa 1 plus 2 ln r upon A, or here we can write it in this form as well, that is h into P and 1 plus 2 ln r upon A. These equations I am writing as equation number 13. Now, what will happen in the elastic zone? So, in the elastic zone your R will be greater than or equal to C. We are going to have this sigma r prime as A plus B upon R square. So, A we obtained as P and substitute the expression for B you got just now. So, minus kappa A square exponential of P minus kappa divided by kappa, and from here you will get this sigma r prime as P into 1 minus h A square upon R square e to the power 1 minus h upon h. Here I have substituted this kappa as h into P, and therefore you will get this form. Similarly, your sigma theta prime will be P 1 plus h A square upon R square e to the power 1 minus h upon h, and sigma z prime will be nu times sigma r prime plus sigma theta prime, and that would be equal to 2 nu p. It's very simple. So, first we will have here as equation number 14 these three equations, and we can write this radius of the elasto-plastic boundary again in the form of this h as a e to the power 1 minus h upon 2h. This equation I will write as equation number 15. Now, what will happen when this h becomes equal to 1? Your equation 12 will become what? Kappa is equal to p, and in that situation what will happen to sigma r prime? That will be p 1 minus a square upon r square, and sigma theta prime is going to be equal to p 1 plus a square upon r square. This you write as equation number 16. Now, this equation 16 which we have derived here, for the yield shear stress of the same order of the magnitude as the applied hydrostatic stress, that means when kappa becomes equal to p, the state of stress in the rock surrounding the periphery of the cavity will be completely in an elastic state. You can have a look here on the equation number 16, and if you just compare the result with the elastic analysis, you will be able to have that idea that right now it is the completely an elastic state. So, in such a situation, when this kappa becomes equal to p, there will be no development of plastic zone around the periphery of the cavity, and the entire rock surrounding the tunnel will be in the elastic condition only. This equation 16 can be interpreted in conjunction with the equation 11, in which C will be equal to A when this kappa becomes equal to P, that is for H is equal to 1 and C equal to A. This suggests that elasto-plastic boundary will shift its position to the periphery of the tunnel, and hence the entire rock which is surrounding the tunnel will be in the elastic state. Now, the variation of both radial and the tangential stresses with the distance from the periphery of the cavity has been shown in this figure. Let us try to see some of the typical feature with respect to this stress distribution one by one. So, here we are taking 4 cases, 1, 2, 3 and 4. The first case corresponds to when H is equal to 0.2, second case is for 0.3, third is for 0.4, and in the fourth case H will become equal to 1. You can see here that it is written. So, when this is the fourth case, as we have seen, this is going to be fully elastic situation. So, as the magnitude of the yield shear stress increases, that means for these 3 values you can see as this is increasing from 0.2 times P to P, the radius of elasto-plastic boundary or the extent of the plastic zone around the periphery of the cavity reduces, because when it is equal to 1, we have seen that it is going to be completely elastic. And that is also shown here that C by A in the first case you can see that it is quite large, which is let us say about 7.3 something here. Then in case of in case of the second case, that is when H is equal to 0.3, it is further reducing, and when this is increased to 0.4, that is H is increased to 0.4, this is further reduced to somewhere close to 2, and when you have the fourth case, obviously this is going to be equal to 1. So, at the periphery of the cavity, what does that mean? That is R is equal to A. So, this ratio R by A equal to 1, and then you can see that here this axis we are plotting R by A, and here it is sigma by P. So, this is what is R by A equal to P. So, we move along this line if we want to see what is the situation at the periphery of the cavity. So, take a look here that this stress concentration factor which has been plotted on this axis, it increases from 0.4 to 0.8 as the ratio of yield stress to the in situ stress, that is kappa upon P, which is equal to H, is being increased from 0.2 to 0.4. So, you see that for the first case here H is equal to 0.2. So, this at the tunnel periphery the stress concentration factor is 0.4. And for this case, when H is equal to 0.3, it increases to 0.6 and further increases when you further increase this H to 0.4 and it increases to 0.8. So, some of these salient features you must keep in mind. Now, even though the stress concentration factor at the boundary of the opening is less than 1, we have seen that it is 0.8, 0.6 or 0.4. The tangential stress at the boundary, when I say tangential stress means I am talking about sigma theta. This sigma theta is less than the in situ hydrostatic stress, which is P. The tangential stresses in the rock beyond the elasto-plastic boundary, they are always higher than the corresponding stresses if the entire rock mass were to be elastic. Try to understand this. If the entire rock mass were to be elastic, this is what is the variation of sigma theta with R by A. See, this is the fourth case. Now, take a look at these respective curves beyond these respective dotted lines. In all the cases, the state of stress beyond this is more than what it was in case of the elastic. So, you see that you drop a line here, state of stress here is more than the state of stress corresponding to the elastic state. So, the initial existing in situ stress gets redistributed in such a fashion that more amount of stress is borne by the elastic rock and lesser stress is left out in the plastic zone. The advantage of this is that if the tunnel is to be supported by an appropriate support system, that support system would be subjected to the lesser load. What happens? All around the periphery of the cavity in the surrounding rock, there occurs the loosening of the rock, and this provides an advantage as far as the economy in the design of support system is concerned. Now, as the rock immediately surrounding the cavity, it enters into the plastic state. Boundary of the opening can deform plastically. These deformations are always going to be higher than the corresponding deformations if the entire rock were to be in the elastic state. That is the reason why stress concentration factor at the boundary of the opening becomes less than 1. Now, this is the typical variation of sigma r and sigma theta at the elasto-plastic boundary. See, this one is for the variation of sigma r at the elasto-plastic boundary, and this is for the sigma theta, while in case of the elastic state, this is the variation for sigma r and this is the variation for sigma theta. Here on the x axis you have C upon A, and on y axis you have the stress concentration factor as sigma upon P. And then one curve has also been shown for this the variation of kappa upon P. You can see here that it is the kappa upon P, that is, this is h. So, that has been shown and it will vary from 0 to 1, and the variation of this has been shown with respect to this C by A by this plot. So, this is what that I wanted to discuss with you as far as the elasto-plastic stress distribution around a circular tunnel is concerned. We could see some of the typical features from this analysis, which was based upon the Tresca yield criterion. So, in the next class, we will learn about some of the failure modes and mechanism in case of the underground excavation. Thank you very much.